test the series. The sum, n equals 1 to infinity, negative 1 to the n plus 1, n squared over n cubed plus 1, for convergence or divergence. So the one thing that's a little bit different is I've written negative 1 to the n plus 1, but that's okay. It's really the same thing as negative 1 to the n minus 1, okay? So what I just said is, maybe I'll write that part here. Negative 1 to the n plus 1, that's really the same thing as negative 1 to the n minus 1.
How is it the same?
I can show you. So this one over here, look at which one has the higher power. N plus 1 is bigger than n minus 1. So I'm going to pull off, it's 2 more. So I'm going to pull off 2, negative 1 squared, negative 1 to the n minus 1. And what's negative 1 squared? 1, so that goes away. And so now they're the same thing. That equation is true, and so the original equation had to have been true.
See, that is what we call the street map right there.
Yeah. Yeah. So I mean, I guess the way I could have demonstrated it here, I really only worked with the left-hand side. So imagine that I wrote it like that. You pull off 2 of them, so I have negative 1 squared, negative 1 to the n minus 1, but negative 1 squared is positive 1, so they're really the same. So it's still going to be an alternating series. That's my point, is that it's not explicitly one of those 2 forms, but it really is. So I can use the alternating series test. So let's start with the limit. Let's go ahead and do part 2 first. N squared over n cubed plus 1. I want to compute this limit. What's my largest degree term in the numerator? 2. The denominator? 3. So 3 is the largest, so I'm going to multiply top and bottom by 1 over n cubed. So you'll get 1 over n for the numerator, 1 plus 1 over n cubed for the denominator, and that limit is going to be 0. 0 over 1 plus 0, so 0. So that's good. I needed that to happen. I needed to get 0 to use the alternating series test. So the only other thing that's left is to show that the b sub n's, right, are decreasing, which remember this is my b sub n here. So that's statement 1 of the alternating series test. So I need to compare bn plus 1 with bn. So n plus 1 squared I need to figure out which one of these is larger. It's not so easy here because the numerator and denominator are both different. So if I cross multiply, then I'm actually going to have to multiply out n plus 1 cubed and n plus 1 squared. That's a lot of arithmetic that I don't necessarily want to do. But decreasing, we've showed decreasing before, right? When we did the integral test. What's another way we can show something's decreasing?
Take the derivative.
Take the derivative, turn it into a function, and take the derivative. So let's go with that here, because that's going to be a little bit easier. So I turn it into a function, x squared over x cubed plus 1. And then I want to take the derivative, use the quotient rule, times 2x minus x squared times 3x squared, x cubed plus 1 squared, and simplify, so you'll get 2x minus x to the 4th and I like when I'm doing these to factor everything I can out of the numerator. What else could I factor out of the numerator? An x, 2 minus x cubed over x cubed plus 1 squared. I'll move that up. And I'm concerned with I want this function to be decreasing, so when is the derivative negative? So we've got these three pieces. The denominator is positive, and so is x, because I'm looking at the interval from 1 to infinity. So it's really only this other piece here that's going to give me a negative. So let's check real fast. If I look at when is that less than 0, and I got to take the cube root, so the cube root of 2. So this function, it's decreasing on the interval cube root of 2 to infinity. Cube root of 2 is a little bit bigger than 1. Right, but this tells me that I'm going to have, at some point, after the cube root of 2, this is telling me that bn plus 1 is going to be less than bn when n is greater than or equal to 2. Okay, so this establishes my decreasing part for me. So that's part 1 of the alternating series test. We've already done part 2. That was the limit we calculated. So both of the parts of my alternating series test hold. I'm able to make my conclusion that this series converges. Converges by alternating series test. Okay, so again, when you're using the alternating series test, you just got to check your 2 conditions. The limit is 0 and that it's decreasing. Okay, yep.
Where did you get the part where n is greater than or equal to 2?
Okay, so the values I'm plugging in for n are whole numbers, right? And I look at this square root of, this cube root of 2, I said that's a little bit bigger than 1, right?
Oh, okay.
So for anything bigger than 1, my function is decreasing, so n has to be greater than or equal to 2. Yes.
Is that how you have to answer it on the test? Where,
You have to justify like your steps on the alternating series test, so you have to justify that it's decreasing somehow.
I'm talking about with where n is greater than or equal to.
Yeah, you would say that because of this.
Yeah.
It's not going to be the same number every time.
Yeah.
Or, I mean, and the other problem, we didn't have to take a derivative because we could do this inequality. It was a lot easier. So you could do the inequality if you can. Okay. Do you have any questions about alternating series test? You know what to check? Decreasing, the limit 0. If the limit's not 0, use the divergence test.